Okay, final exam is coming up soon. Final exam is 70 multiple choice questions. I know some of you have the ACS prep guide. If you do not, I highly recommend it. It's carried in the bookstore here. It's grouped. Chapters are a little bit different from standard chapters. Chapter 1, structure, hybridization, resonance and aromaticity. Chapter on nomenclature, chapter on acid bases, chapter on stereoisomerism, chapter on nucleophilic substitutions and eliminations, on down the road. Oxidation and reduction, spectroscopy. It's a good resource. ACS exam, we'll talk more about it. Hopefully you're getting to start really reviewing and getting ready for it. It's your big opportunity, yeah? Passing out here a permission to post your score. If you score 90 percentile, I would like to post it in like a department newsletter or maybe a department plaque if we ever decide to do that. If you want to get permission to include your name with your high score, please turn this in. Next Wednesday. I'll collect those next Wednesday.
Question about the multiple choice.
Question, multiple choice, what page?
Page 48, number 8.
Page 48, number 8.
Asks about reacting acid chloride with some reagents, and then it says, it asks what sort of alcohol it would yield after hydrolysis. Does that mean like you perform this reaction after hydrolysis, or does this mean that you perform this reaction and then hydrolysis?
So you perform the...
Like, does the hydrolysis happen before or after the reaction?
I think after the reaction. It's an odd terminology. Hydrolysis is really, that's aqueous workup is what it's referring to. If you add water, I don't like the terminology.
Okay. Thank you. All right.
Okay, we have a variety of things. I'll say a few miscellaneous things. A couple of previous handouts. For example, here, one of the earlier acid derivative handouts, there was something about anesthetics in dentistry. Anybody pre-dental, like go to dental school? Okay. Here is some anesthetics used in dentistry. You've heard of Novocaine, etc. These are very similar. These four here are all amides. I mean, that could be maybe the principal functional group. Of course, it's got aromatic rings, it's got amines, etc. But amides. Please read the questions. This is a very good application of textbook organic chemistry. Please read the question down here. This is Novocaine here. Novocaine is actually an ester. Okay? Please read about this. Try to answer those. We'll look at those maybe on Friday. We'll look at the condensation polymerization at the bottom of that page. Show the monomers. We'll look at that on Friday. Carbonyl and IR. Any questions about IR? How are we doing on working those IR problems? Any questions about IR? No questions? Okay. Any questions about acid-base extraction? Okay, let's begin today. Simple additions. Hopefully we'll be able to answer this question here. If you haven't already, let's see where we left off at. Test on Monday, right? Okay. 3 different reactions to give this alcohol here. How'd we do? Somebody have one? I'd like to show maybe on the overhead. Somebody have one we can show on the overhead? Anybody? 3 different reactions to give this alcohol. No? Okay. Let's move down here then. LEH, we did this, gives aldehyde. What does this give? Not an aldehyde. Addition elimination gives aldehyde, but then we added again to give, what was the final product there? Actually, an alcohol. The reaction does not stop at the aldehyde. If you want to stop at the aldehyde, you can, but you have to use what's called Dibol H. We'll stop at the aldehyde. Dibol H is another hydride source. We'll call it a weaker hydride source. Also done at cold temperature to keep it from being so reactive. Dibol, let's see what it looks like. It is aluminum, that's the Al. It's got an H. D, diisobutyl. These are isobutyl groups. There's Dibol H. It's an aluminum hydride, but it's neutral. It's a neutral aluminum. It is a hydride source, though. You might say, well, why would this aluminum want to kick off an H in the electrons? It's not negative. This is a Lewis acid. We used AlCl3 as a Lewis acid for Friedel-Crafts reactions. Something will coordinate with this aluminum. Maybe even the lone pairs on one of these guys. Once lone pairs that coordinate with it, the aluminum becomes minus. Then the aluminum's mad and it says H, you take a height. Okay? But it's weaker because it's not fully minus. What's another reason it's kind of weaker? May not be obvious, but steric effects. The isobutyl groups make it sort of sterically hindered a little bit. So it is a weaker hydride source. H minus, electrons add, electrons up, back down, keep that off, okay? Taking a shortcut here, mechanistically, there's an intermediate, right? What does that give? Aldehyde. And that's it, game over. You can stop at an aldehyde if you use a hindered hydride source. Let's call it this. I usually say that more. Hindered or weaker. I use that terminology more. Hindered hydride source, you can stop at the aldehyde. If you use LEH, you don't stop here. It'll keep going, hydride will add again, and you'll end up with an alcohol after aqueous workup. Okay, 6, how do we do on that one? Somebody have an answer for 6? Should have been pretty straightforward, very similar to 4.
So just I instead of H. Yeah.
Somebody have an answer for 6?
Is negative.
Answer for 6? It's, you only added once. You gave a ketone. Ketone's going to, Grignard is going to add again. This is analogous to reaction 4. It's going to add twice.
So it's here, die.
Going to add twice. Where did the H come from? Where did the H come from that's on the alpha carbon? Mechanistically, there's nowhere that it could have come from. Where's the alpha? Where's your ethyl group? So what? Ethyl? You added an ethyl in your mechanism, but then your product doesn't have an ethyl. Anybody else?
I thought that it was going to be the hydrogen.
You just did a single additional elimination to give a ketone. It's going to add again. It's going to be like number 4. Look back up at number 4. After the hydride added and kicked off the chlorine, then we added again.
So it does this thing.
We're going to add twice, just like number 4.
How would we know?
Yes, aqueous workup. Aqueous workup is going to make that neutral. Put a proton on. Anybody? Anybody else? Samba?
Will that be similar to a Grignard?
This is a Grignard. Ethyl lithium reacts just like a Grignard. Ethyl lithium is ethyl minus, lithium plus. But these are ethyl anion sources. This is the type of question where we really don't need to go over it, other than letting you know that it's going to add twice. Okay?
Why would we, like, I would not have thought of it, why does it add a second time?
Okay? That's a very reasonable question. To have the ketone and then say, well, why does it add again? Very reasonable. What's not reasonable is to have nothing there, blank. Okay, guys? Here we go. These are sources of ethyl anion, right? Ethyl lithium also. Electrons add. I would draw this out. That's not good to use it. It's a problem. Ethyl anion, right? That's how these react. This adds here. Electrons up. Boop, 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 boop. Electrons up. Minus. The Cl there. And now there's an ethyl there. Not a methyl. Ethyl. Electrons back down. Where we're going to kick off? Chlorine. Duh. And what does that give? Ethyl ketone, not methyl ketone. It's all in your mechanism. We don't have to. We don't pull products out of the air. We do mechanisms and say, "There's your product." Okay. Just like number 4, when we did this with hydride, and we had a carbonyl with an H, which we call an aldehyde, we then add it again, right? Same thing here. Grignards are going to add twice. The only time these reagents are not going to add twice is when it's a unique reagent. Like Dival, it only added once. Why? Because it's a hindered hydride source. And we also are doing it very cold to keep it so it only adds once. Grignard adds twice.
Do you add twice because there's still a partial positive charge on the carbon?
But what's a carbonyl? And Grignards react with ketones. I would refer you to question, well, number 3. It's reacting with aldehyde. Aldehydes, ketones are the same thing. Grignards react with aldehydes, ketones to do what? Electrons add here, electrons up, so that gives what? Electrons up is going to be minus, and what's on this carbon here, the original, the alpha carbon? Ethyl and what else? Exactly. Somebody showed me a product that essentially had an H here. Because there was nothing there, I assume it's an H. And then I asked, where did the H come from?
So from the P-chem way of thinking that...
But before we get there, this is not an H, is it? What is it? It's another ethyl. Again, mechanism gets you your product. You don't just pull things out of the air. Now, are we going to reform carbonyl? No, you're not going to ever kick off a plain carbon or a plain hydrogen. These are just plain alkyls. No, that's it. Game over. The only thing we can do is work up. Aqueous workup. Very top, it probably says assume aqueous workup. Aqueous workup is going to do what? I'm not going to redraw it. It's going to put the H on. It's going to protonate the alkoxide. There's your product. By the way, some people will say, hey, you got to memorize it, you get a tertiary alcohol. Tertiary alcohol, right? Please don't memorize that. No mechanism, and then say, yeah, it is a tertiary alcohol, so what? Pardon?
For the Keegan way of speaking, the carbanion is much less stable than an oxygen with a negative because it's oxygen.
Yeah, I mean, that's a very strong anion base. This is all driven this way. And once you get to the anion, it's not reversible because you're not going to kick one of these groups off. Okay, Grignards add twice. Regular hydrides add twice. Dibol H only adds once. What if you wanted to stop at the ketone? Is it possible? Not with a Grignard or lithium or alkyl lithium, not possible. But there is a reagent. This guy here, it's called an organocuprate. If you use an organocuprate, you can stop at the ketone. I don't think we've seen organocuprates before. It's a copper-based reagent. It's less reactive than a Grignard. What's the structure of this? If we draw it out with a copper, 2 ethyl groups. Of course, these can be a variety of R groups. In this case, they're ethyls. And then a lithium. We draw it ionic, that's plus. It means something's minus. Well, copper is minus. I know in Gym Chem they tell you copper always has to be plus, right? Well, I mean,
It's a lot.
it's minus here.
It's a lot.
Now you could say, well, how do we calculate charge? Let's not get into that, number of lone pairs. But knowing it's minus, let's keep track from there. For example, if it loses an electron, it's going to become neutral. But the copper's not happy. It would actually prefer to be positive. It's like, hey, R group, carbon, you and your electrons take a hike. So when this carbon and the electrons take a hike, it essentially R, I mean something bonded to it, and 2 electrons, so R minus source. This is a it's like a Grignard. It's the alkyl anion source. Copper shoots off these R groups with the electrons. Again, this could be ethyl, propyl, butyl, hexyl, phenyl, I mean, okay, R groups. This is called an organocuprate because an anion of copper is called a cuprate. And it's organic, so it's organocuprate. Very versatile in more sophisticated organic chemistry. How do you make organic cuprates? You actually make them from like alkyl lithiums. Something like alkyl lithium. This is copper plus. You have ethyl anions adding. If you add 1, that gives what? Copper with 1 ethyl. But actually, these metals can be Lewis acids, and you can get another one adding. You get 2 on there, and that's actually becomes a minus charge here. The lithium will sit with it. We actually needed 2 of these, so we used 2 of these. 1 lithium sits here, the other lithium sits with what? Lithium iodide would be a byproduct. Okay. It's some type of stronger alkyl anion reacting with the copper, and you generate this. Once you generate this, these are less reactive alkyl anions, but they still react as alkyl anions. In the end, it's called an organocuprate. It's also called a Gilman reagent. Chemists who develop these reagents a good bit. So with all that, what we know is that Gilman reagents will only add once and you can get the ketone. Now they actually also only react with acid chlorides. They don't react with like esters. But we have this guy here, electrons here, electrons up, back down, take that off, and we get our product. This ethyl ketone.
Is this assuming we only have one EQ, right?
Only have what?
Like one equivalent? Because if we had like excess, it could be moved over again.
I don't know that excess will add. Not sure. This doesn't really require cold temperature. I don't know. I don't know that excess will add to this. In the end, what we can say here is you get a very good yield of ketones this way. Replacing the chlorine with an R group from a organocupric. Not a Grignard. If you do Grignard or alkyl lithium, it's going to add again. And you'll end up with a alcohol after workup. Organocuprates only add once. A very great, very nice way to make ketones from acid chlorides. Okay. Let's look at some reactants over here. We got this amide with LAH. Can you predict a product here?
Yes.
Someone have a predicted product for this one? Predicted product. Someone have something? Anytime you can reform carbonyl, kick off the leaving group, that's typically easy to do. Can you envision doing that? That's one thing to keep in mind. Such a product is just not stable. It's going to lose, it's going to want to reform carbonyl. Where did the methyl group come from? There you go. That's a reasonable product, but LAH reacts with aldehydes, right? Like question number 3 or 2 or 3. If you make a product that's going to react with your reagent, you should react further. That's very reasonable. Workup is going to give a neutral product. Problem is, while that's very good mechanistic thinking up to this point, it's actually wrong. Because we're going to have a twist. But that's what I expected to see right there. Just protonated, workup.
Will NH2 leave?
Will what leave?
NH2? Like, is that can you do that as a leading group?
Carbonyl chemistry, sure. Have you ever seen a nitrogen B minus? Sodamid, we've never seen sodamid. Sodamid is a common base used for deprotonation of alkynes. Hopefully you've seen it. If you've ever seen a minus, it can leave in carbonyl chemistry. I mean, if you hydrolyze this to with hydroxide to the carboxylic acid, the nitrogen has to leave, right? If you hydrolyze this to the carboxylic acid, which we know you can do, doesn't the nitrogen have to leave? Hydroxide, add up, down, kick off the nitrogen. That's hydrolysis to the carboxylic acid. So instead of hydroxide, we have hydride, right? So, boom, boom. Okay, here's the product. The product of this reaction is your benzene ring and you get this primary amine. Primary amine. Who got this right?
So that just leaves?
Primary amine.
Did you have to do rest?
What happened to the...
Came off?
What happened to the oxygen?
It just said bye.
It apparently served as a,
Leaving group?
yeah. Instead of the nitrogen leaving, the oxygen leaves. This is a little unique. Let's see if we can work our way towards how this happens mechanistically. First, hydride adds.
Obviously, it can't come back down. Oh, wait.
It's there, right?
Yes.
Plus what? What else is here if we consider everything else? After the aluminum hydride gives up,
Lithium, aluminum.
if this gives up a hydride, what does it become?
Plus.
Yeah.
Minus.
It becomes just AlH3, right?
Yeah.
AlH3 is like AlCl3. AlCl3 is a Lewis acid we use for Frito crafts. You got Lewis acid here. Now, focus on here. What has to leave? Oxygen or nitrogen? Oxygen has to leave. That's a terrible leaving group, even for carbonyl chemistry. Propanate, we have no proton. We're not under acidic conditions. We don't have a proton acid, but we have a
Lewis acid.
Lewis acid.
And now
By the way, what does not happen is, now it could, if this is hydroxide, we do this. This apparently does not come back down and kick off the nitrogen. Apparently it does not, because if you kick off the nitrogen, you're not going to get that product. So it doesn't do the standard come back down and kick off the nitrogen. Nitrogen is like, hold up here now. You know, I'm not a great leaving group. And instead, the oxygen is like, well, instead of making a bond here, I want to make a bond in this Lewis acid. We get this. Now, I'm not going to keep up much with the fate of this, but at this point, this becomes another hydride donor, because now we made the aluminum bad. It starts getting more hydride. But let's don't worry about that. In fact, if we give off a hydride, we can make that neutral to make this next step better. What happens is the nitrogen says, hold on, you're not kicking me off.
I'm kicking you off.
I'm going to kick you off. We're not kicking off a negative oxygen as a 2-, we're kicking off a neutral oxygen because it coordinated with the aluminum. Now again, this can give off hydride and go neutral, but when we do that, we get double bond in. We can draw these H's here. There's one H there, that's that one, I just drew it upside down.
And then
Plus aluminum. I'm just going to call it X. I mean, this guy can lose H's over here. Let's don't worry about that. Oxygen gets kicked off as an anion. What do we need to do to get home?
lithium, aluminum.
Now, I'm going to cringe a little bit because we got an acidic proton here. But if this adds here and moves these back, because that nitrogen wants a long pair, what does that give?
Product.
Yeah, there's your product. Now, don't tell anybody I said this, but I would prefer for this H- to take one of these H's because those are acidic H's at this point. Then you come back with a hydride and add to the neutral and do that route. But books will show this because books often gloss over acid-base chemistry. But H- is a pretty strong base. You've got one that looks like a proton here. Okay? In the end, we turned the tables. The oxygen left, but it coordinated to the aluminum there. And this is the outcome here. It's an unpredicted outcome because otherwise you might think this is going to come back down and kick off the nitrogen. You give an aldehyde, and then the aldehyde reacts again. So, ultimately, what do we do to the primary ambient? Think about it. Look at it. We just removed the oxygen and turned that into a CH2.
You reduced it.
We got rid of the oxygen and turned it into a CH2. We deoxygenated the ambient to the primary amine. It actually doesn't have to be a primary amide. You can have substituents here, and so it doesn't have to be a primary amine. So a little neat reaction. Probably the first person to ever do this was expecting to get like an aldehyde or an alcohol product. Instead, they got an amine. They're like, where'd my oxygen go? So the nitrogen leaving, the oxygen leaves. Okay, hopefully at this point you're recognizing that, hey, it may look weird, but it's pretty sound principles that make sense once we see it. Okay, nitriles. Nitriles will react with LAH. Actually, it may be easier to predict if you consider hydrogenation, like with H2 and maybe like platinum or nickel. LAH gives the same product. This illustrates the general idea of what you can do with a nitrile in terms of reduction. Both of these cases we're adding hydrogen, reducing the nitrile. Here's the nitrile coming off, which is analogous to maybe an alkyne, a triple bond. Well, what does hydrogen do to an alkyne?
Breaks it. Takes it down to a double bond.
You first get the alkene, right? If you had geometry or cis-trans, it would be cis or trans? Cis. It'd be cis. But then if you keep going with a regular catalyst, what do you get?
The alkane.
You just reduce it all the way down to the alkane. Same thing with the nitrile. So forget about LAH. Hydrogen does the same thing as for alkynes. So show the product if you reduce it down all the way. What does it become?
Double on H doesn't go all the way down.
You get this primary amine. Keeping track of your carbons, right? 3, 4, 5. 3, 4, 5. This C and N here used to be what? Triple bond. But we added H's and that became H. Well, let's say there's an H there and we show our H's on nitrogen. Then we added another H here and here, and it became CH2H2. It's a hydrogenation of the nitrile all the way down to the primary amine. Well, LAH gives the same product. LAH is going to be more of an ionic mechanism where you have hydride, and this does some chemistry like this. And we do a nucleophilic addition to the polarized pi bond. What would you do next here? There's no H plus, that's not acidic. An H on a carbon is not acidic. Hydride again. And move electrons make 2 minus.
You hydrate.
We need another hydride in here, but you don't want to make that 2 minus. This probably coordinates with aluminum hydride. Okay. Now we can come in with another hydride source. I'm drawing in the H's here. And so we get the carbon with 2 H's now. And this becomes like this. And this is an anion. This has got to pick up H's. This is going to pick it up from aqueous workup. The H's would have to come from aqueous workup. Because you got, in this case, you have H minuses, but then you need H pluses to go on the other end. Where with hydrogen, we know it's sort of, the old two H's from the metal coming in. But we see the idea again of the aluminum coordinating with the nitrogen, so we never created an N2 minus. N2 minus would be pretty high energy. Nucleophilic addition to a polarized pi bond, complexation with Lewis acid, then a second, because this continues to be a polarized pi bond. And then when you add in water, this is going to start picking up H's, right? This gets hydrolyzed off.
It just comes off.
Not really going to get into it. Water attacks the aluminum, kicks off the nitrogen. We're kind of going to gloss over that. Aqueous workup will give you the protons and remove the aluminum. Question?
Why is it complex in the family in the first place? Why not just go ahead and do it?
Because there's no water at this point. The workup is at the very end. You can't. If you have LAH and water in the same class, you're going to have 5. Not compatible. There's no water present at this point. This is the end. Then you add in the water. Put them on. LAH is very reactive.
How do you get rid of it?
How do you get rid of what?
The LAH, I imagine you having a root capsule.
When you add water, you're eventually going to end up in like the aluminum hydroxide. The oxygens are going to end up bonded to the aluminum. Aluminum's a Lewis acid, water keeps adding. The hydrides keep getting shot off. You got to be careful though, because if you shoot them off too fast, you're going to create hydrogen and fire and stuff. Dibol H, well, guess what it's going to do compared, now that we saw the above one? Dibol is going to only maybe add once. Where could we stop at?
The complex.
Instead of adding twice, stop here. Which would be what type of product? If we have, okay, we're drawing the H, this became minus. It added once, that became minus. This is complex, but if we say it only adds once, it's sort of, this is it. It only adds once. What's missing from both of these is aqueous workup. If you have such a structure, whether it's complex or not, you're going to get the same thing. If we add in aqueous workup, what's the product going to be if we just put proton on? I'm going to draw it with just pure line bond, carbon, double bond N, and what's on the end? H. There you go. There's a new H here. That new H came from your hydride source. Here you go. What's the name of that functional group? I don't think we've seen it before in lecture, but you've all made one in lab. Imine. Imine. What is the corresponding carbon double bond O called? Generic, depending on what's here. Carbonyl, right? And imine is where you replace the oxygen of a carbonyl with a nitrogen. And the nitrogen, since it's trivalent, it's going to have one more thing bonded to it. It could be an H or it could be an R group. Imine is a nitrogen analog of a carbonyl. Of course, carbonyl is not a precise functional group. Many functional groups contain the carbonyl. Imine, carbon-nitrogen double bond. Carbon-nitrogen triple bond would be what? cyanonitrile.
I mean, that was on, we're getting one functional group.
And a carbon-nitrogen single bond would be like an amine, amine. Whenever you say amine, a lot of times you have to say, what? Amine is one thing, amine is another. Now in biochem, you will not call them amines. You will call them what? Biochemists call amines Schiff bases. Apparently some guy named Schiff, I think it was a guy. But this lone pair is basic. It's not an p orbital, it's not highly basic, but your body uses the lone pairs of amines as bases in many biochemical processes. It's an sp2 lone pair, it has some basis, it's not in a p orbital. And you'll use it as a base in biochem. You'll call it a Schiff base. Amine. Okay. It says stop here. This is usually not isolated though. It can be, but very often this continues on. Hydrolysis of the amine. Okay? And that is test 4. Hydrolyzing amines. Back to carbonyl compounds. And that is a good ending point for test 3 material. We will see that here we made an amine by partial reduction of a nitrile. In lab, you made an amine by reacting an amine with an aldehyde, which is traditional amine chemistry, test 4 chemistry. We'll see amines during test 4. Okay, there's some ones to work below. Please work those for tomorrow. I'll see if there's any questions about them. If you would like to ask questions, I hope that you would. Would you like to work one of these today? Sure. Anybody? 1, 2, 3, or 4? 1. Number 1? Okay, what's product number 1? You show product number 1. Where'd your methyl go? Somehow you replaced a methyl with a hydrogen. Nobel Prize.
Oh, you're right. No.
Keep going. Keep adding. Yes. First you get a ketone, then he keeps adding. It's not going to reduce the benzene rate.
Ask him in a second. If that's not right, then I...
Dr. Stevens, is this
Dr. Stevens.
I'll show it.
Well, mechanistically, we have a phenyl anion, right?
Yeah. Almost right.
Here. Are we going to react with carbonyl or are we going to react with aromatic ring?
Carbonyl.
I mean, what type of chemistry would you do with the ring? I mean, this is a nucleophile. You can only do NAS or benzyne. NAS requires a strong electron. I mean, what leaving group do you have for NAS? Not really. Benzyne requires very high temperature. Carbonyl chemistry is much more readily going to happen. This is carbonyl chemistry. I can give you a reaction where you react here, here, or here. For example, we could brominate this ring. And the bromine would probably go where? Ortho to the methyl? Or pair to the methyl? We can do a benzoic bromination over here. Okay? Final exam, you're going to be looking, okay, what reaction am I supposed to do here? You got to be careful about just doing, okay, carbonyl chemistry. Because when you have many options, you have to be able to decide, well, what am I reacting? But hopefully you can think about it and see that this is it. And we're going to get electrons up. And we have a methyl there, not an H. And we have a phenyl here. Now the phenyl's a benzene ring. You can draw that out if you want, but pH is okay. All right, is it going to come back down and reform carbonyl? If it can, it will. But are we going to kick off any of these groups there?
No.
No. Game over. That's it. All you can do is throw in water and extract or something. What are we going to get? You're just going to protonate with some type of aqueous workup or acid. I mean, there you go. You got that tertiary alcohol. Please think mechanistically. Just like math. 58 times 29, who cares? Do it, there's your product. Okay? You don't pull math answers out of the air. You work, you use your understanding. Okay? Please do the others. Okay. I forgot to pass back Wendy's summary table, which was this was a pretty nice summary table right here. Yeah, that's it. Some people gave me 3 pages. The summary table asks for what? It asks for product, observed melting point, literature melting point, yield, and appearance. There it is. Nice, simple summary table.
Because of improper.
Okay, I know interpretation of directions maybe aren't always the same, but is asked. Okay. Yes, please.